Welcome to the lecture on metamorphic rocks. Metamorphic rocks are other rocks that have been changed by heat and pressure. Not enough heat to melt them because that would make an igneous rock. Here are the objectives for the chapter. Tell how metamorphic rocks form, tell where they form, identify 5 metamorphic rocks. I could show you pictures of these in a quiz and you should identify them. Identify how rocks change from one to another. That's a fancy word for it. Identify some common features of metamorphic rocks. Sort them by type, foliated and unfoliated or massive. Describe how they're important to us economically. Explain how they're related to plate tectonics. Identify some local rocks. And insert metamorphic rocks into the rock cycle eventually. Now, this is the second time I have done this lecture. First time went a little bit long, so here we go again. This is what happens when you take a piece of granite, you grind it down until light can shine through it. You can really do this. Stick that thin section onto a microscope slide and then name it a thin section and shine polarized light through it. You see all the crystals in there. That's a typical igneous rock. Here's a typical metamorphic rock. Well, what a difference. In here, the minerals are jumbled. In here, they're kind of all oriented the same direction. Something must have caused that. Something must have caused this, too, under polarized light, this thin section. Wonder if this rock is any hint. Here's one way that metamorphic rocks form. You know that if you take a box, you stick it under the water, and then stick it further under the water, it'll be compressed by pressure. The same thing happens to us. If you ever dive underwater, you realize this happens to your head, your ears. If you saw a recent 60 Minutes on the deep water divers, you saw their faces get a little bit weird. Pressure can do strange things. Now, this is just water. Imagine having earth on top of you and having pressure about 1,500 times as great as the pressure that we're under right now. We don't think about it. Consider a dough ball, like Play-Doh. You can either squish it with pressure from left and right, or top and bottom, or fore and aft, or you can shear it. Both of those are forces that rocks undergo underneath Earth's surface. Now imagine there are minerals in here. What's going to happen to minerals if you squish from side to side? The minerals are going to be lined up perpendicular to the direction of force. If we do this kind of thing, what's going to happen to minerals? To help you imagine this even better, imagine there are sequins in this Play-Doh. The sequins in the Play-Doh here would be oriented vertically, or almost vertically. The sequins in the Play-Doh here would be aligned left to right. Here's another example. Take your Play-Doh with sequins in it, squish it from left to right, and you get layers kind of like this. If you shear it with your hands going left and right, or right and left, you end up with this kind of things, and your minerals become elongated. In foliated metamorphic rocks, I'll show you pictures of these in a while, this is what happens. The minerals line up. Here's a crazy example, and these aren't minerals. This is conglomerate. Under pressure and under shearing, this can be warped under heat and pressure, but not melting, into this. This is called stretched pebble conglomerate. This is so cool. Okay, once again, metamorphism requires hot temperatures, 150 to 200 degrees Celsius for minimal metamorphism, and pressures up to 1,500 times that of atmosphere. You can take these temperatures higher if the pressure is high. You can get them up to 6, maybe 700 degrees Celsius without melting if the rock is under a lot of pressure. But as soon as you release that pressure, it's going to melt. Okay, where does metamorphism occur? Well, duh. Where are you going to get really high temperatures and pressures? Not on the surface. It has to be way down deep. And in one case, it's where you have a magma body, a pluton. When a pluton intrudes into a rock, the rock around it gets baked. In the case of limestone, it will be baked into marble. If this were sandstone, it would be baked into quartzite. If this were basalt, it would be baked into hornfells. Whatever rock is there can be baked into another type of rock. Something else happens. There's water released in the cooling of a pluton, and that water will gather minerals, and because it's hot, will make its way up. Those minerals or those ions will be deposited up above this pluton. I'll show you examples of that in a while. It's very handy for Arizona. Here's an example of a pluton under a mid-ocean ridge. This pluton has water escaping from it in the cooling process. This water going up brings minerals with it, and on the bottom of the seafloor you can see these weird tubes called black smokers. Now, water from the seafloor comes down to take the place and brings minerals up with this. This is kind of a more complicated diagram, but it shows you that near the surface you get less metamorphosed rock. Phyllite is slightly more metamorphosed. Schist is more metamorphosed. You know what I mean. And gneiss and migmatite are really metamorphic rocks. So if you find these kind of rocks, you know they started way down deep. Now you can get sedimentary rocks that are folded. Just because they're folded doesn't mean they're metamorphosed. Remember I was talking about water escaping into rocks a while ago and taking minerals with it? Here are little plumes of quartzite. Why is this important in Arizona? Well, gold has an affinity for quartzite. So if you find little veins of quartzite, often, well, okay, often at least in my mind, you'll find gold. Now, how is this related to plate tectonics? Anywhere inside of this zone here, because it's under pressure, 300 to 600 degrees Celsius, and I know that's hotter than I said earlier, but again, this is under pressure, so it's not melting. You're going to get metamorphic rock. Down here, you're going to end up with melting. In here, something in between. So the sliding of one plate beneath another causes metamorphism. Also, the escaping of hot water from subducting rock also causes metamorphism. First, let's look at non-foliated rock. It's a little bit weird. I should explain what foliated is first, but I'm going backwards. Think of non-foliated rocks as just one rock that's the same thing all the way through. Hornfels. It's kind of quartzite and some feldspar all the way through because it's baked basalt. Take sandstone, which is really made of little pieces of sand, nothing more than silicon dioxide. In the case of this sand, it comes from right down here at Coral Pink Sand Dunes National Monument. If you squish sand, it turns into quartzite. This is one view of it. It's mostly silicon dioxide with some stain. Here's quartzite. You can see this out north of the McDowells. There are peaks made out of this because it's so resistant to weathering. Here is a town named Quartzite in Arizona, and here is a monument to a Jordanian fellow who worked for the army transporting stuff by camels. His real name was Haji Ali, and he was a captain in the army back in the 1800s. But Americans, being Americans, couldn't say Haji Ali, so they called him Hi Jolly. And here's a monument appropriately made out of quartzite to him, although the bottom is really basalt and igneous rock. Here's quartzite, and you can see the bedding planes of sandstone still in this. Cool. Now marble. Marble is made from, remember I showed you this before? Marble is made from limestone that has been baked. If you have a pluton and it bakes the limestone, you make marble. Now, this is important because if you put a drop of acid on quartzite, you're putting a drop of acid on silicon dioxide. It won't bubble. If you put a drop of acid on marble, it will still bubble or effervesce. Also, because marble is made of calcium carbonate, its hardness is not much more than 3. Quartzite has a hardness of about 7, being as it's made of quartz. 2 ways to tell them apart. So marble comes from limestone. Sandstone forms quartzite. Here is limestone that could, if it were underground a little longer, have been made into marble. Why do we use this? Well, we grind it up and we make it into cultured marble. This is, by the way, real marble. I shouldn't be talking about cultured marble now, but I'll show you in a minute. Regional metamorphism. If it's not just an area that's heated, but an area that is, boy, am I out of order, undergoing plate tectonics, that's called regional metamorphism. By the way, this is a mine, I forget where it is, and this is where they mined some columns for some of the buildings in Washington, D.C. It's now a historic place. This, I don't know, tragic accident, sorry about that. Cultured marble. Remember that limestone I was showing you? Well, you can take marble dust or limestone dust, mix it with epoxy, and make something that looks like this. It's called cultured marble. It's not really. We add some dyes and it looks like real marble. People even paint to look like marble. This is real marble. This is in Agra, India. This is the Taj Mahal. It is a tomb for some fellow's wife. Now, people that like marble really get into it. In particular, hey, here's one, the island of Paros. I have a piece of this Parian marble. It is from the mine where the Pieta marble originated. I was down in there wandering around, found this beautiful marble, brought it out, and just read about it later. And I just noticed today, when I was doing the lecture the first time, Knox and Blount County in the United States have marble. My mother's grandparents had a marble quarry near Friendsville, Tennessee. How cool. But there are all kinds of marbles. Notice that the Mediterranean area, which was once a shallow sea with lots of coral, became home to limestone and is now home to lots of marble. Again, here's quartzite. It's massive, not foliated. Here is asbestos, which is formed in quartzite, and there are little pieces of a silica-rich mineral called asbestos. Now, when water gets under the ground near these hot bodies, it brings materials with it. It'll dissolve metals. The metals will come up with the water. As the water leaves, the metals are left behind. So that if you fly over this area, you'll be flying over normal land, normal land, normal land, and then right in this area, it looks like it's rusty. Well, it is, because all the metals that make up this soil have oxidized. So miners actually use satellite images now looking for what are called iron hats. Here are the black smokers that were under the ground. And this is why this kind of thing is important for Arizona. Hot water bringing up minerals has created these big areas that we go mine. Arizona used to be one of the biggest sources for copper mining. Right now, we are mining rock that is only 0.5% copper. How concentrated is that? That means that for every ton, 2,000 pounds you dig out, you get 10 pounds of copper. Let's say you get $1 a pound for copper, getting $10 for moving that ton. You have to be really good to make a profit at this. This is a quick and fairly complicated list of metamorphic rocks. Limestone and dolomite can change to marble. Quartz can change to quartzite. Shale and basalt can change to hornfels. Now your book the book here screws up a little bit. Shale and basalt and hornfels can change to slate. Slate can change to phyllite. Phyllite can change to schist. And schist can become gneiss. Really? Yeah. I think I'm overlapping the second lecture, but I'm doing so well I'll just keep going. If you get to the second lecture and you've already heard part of this, just advance through it. Remember we talked about squishing the rocks and everything lining up? Well, these are foliations. If you have leaves drop on the ground, we call it foliage. In fact, the leaves on the trees are foliage. The leaves in the metamorphic rock are said to be foliations also. Here is slate. If you tap slate, it really sounds like a rock. If you tap shale, it sounds like compressed mud. You don't want to use shale as a tile for either your floor or your roof because if water gets on it, it really smells like mud and begins to fall apart after a while. Compressed shale, however, turns into a solid rock which is impervious. And that's why back in England and back east, they make roofs out of tile made of slate. I can talk. And the slate tiles here are just beautiful. I think I'm going to stop here because I think we get to this in the second part of the lecture. So, stop here.